Hello everybody and welcome to the second episode of our series Bayesian Inference, and in today's video I will discuss with you the topic of Bayesian data modeling. And to kick off, I would like to give a short introduction about the term data modeling in general. Data modeling has a lot of definitions, a lot of interpretations depending on the context field of IT that you are talking about. But specifically, when we talk about the context of data science, what we mean by data modeling is to find the best function that describes our data observations or data measurements. So for instance, if we have two variable data set, for instance between the height and the weight, and we decide that these observations are linearly correlated, then the data modeling of these two variable data set is to find the linear regression function that best describes the relationship between both variables. In the same way, if we have a data set like this and we understand that the variables x and y are non-linearly or polynomially correlated, then the data modeling we are talking about here is to find the nonlinear function that best describes the correlation or the relation between both x and y. So this is what we mean when we are talking about the term data modeling in the context of data science in general. Now let's move to the Bayesian data modeling and what we mean by doing data modeling in the Bayesian manner or in the Bayesian approach. If we start by putting the Bayesian theorem once again, we see that the definition of Bayesian theorem is that the posterior probability, which is the estimation value or the prediction value we need to identify, is equal to the likelihood probability times the prior probability divided by the marginal likelihood probability. In most of the Bayesian inference applications, we usually ignore the marginal likelihood probability simply because this is a model independent parameter. It doesn't have anything to do with the modeling itself, with the parameters that you are looking for. Therefore, we ignore this term in our equation, and because of this, we define the posterior as it is proportional to the multiplication of likelihood probability and the prior probability. And this proportional relationship is very important, and I will explain why in a while. So basically we have two basic approaches when we talk about Bayesian data modeling, or when we talk about data modeling in general. The first approach is called frequentism. The second approach is called the Bayesianism. You can think about frequentism as a special case of Bayesianism, or Bayesianism as a generalization of frequentism, but at the end of the day, we usually handle our data and analyze our data using one of these two main approaches. So what is frequentism? Frequentism is a 100% data dependent approach, which means that within the frequentism approach, we draw our conclusion, we draw our estimation using only data observations or using only measurements that we have at hand. We have only one source of data modeling, which is the data itself. And the definition of the posterior in this case will be only dependent on the likelihood, because the data is usually represented within the Bayesian or within the Bayesian definition using the likelihood. So when we draw our estimation using only data, we will consider the posterior is only dependent on the likelihood probability, and this technique is called the maximum likelihood estimation, or MLE. On the other side, the Bayesianism depends on two sources of information to draw the required estimation, or the posterior estimation. We use the first source, which is the data, and we use a second source, which is, we call it as an expert, which is the prior estimation, or the prior probability distribution that we employ beside the likelihood distribution in order to draw our posterior estimation. So in the Bayesianism approach, the posterior is proportional to the likelihood and the prior, the multiplication of the likelihood probability and the prior probability. And this technique is called the maximum a posteriori, or MAP technique. This is the main two approaches that you may think of if you want to do some predictive analysis tasks. You may use the frequentism, you work only with data, or you can use the Bayesianism, where you can use the data observations plus another source of information, which is a prior knowledge or an expert opinion that you can merge into your equation and draw your estimation. Of course, in real life applications, the expert part, or the prior distribution, must not be an explicit opinion of some expert. It can be a single observation of the data that we excluded from our data set and treated as a prior knowledge in order to build our Bayesian data model. But this is how we understand the Bayesianism, and this is the way we distinguish the Bayesian approach of data modeling from the frequentist approach of data modeling. Now let's revisit our Bayes theorem. We defined it in the previous video. The probability of the posterior, which is the probability of the hypothesis given the evidence, is equal to the probability of evidence given the hypothesis times the probability of hypothesis divided by the probability of evidence. We may rewrite the formula in order to be more practical and more usable in our real life applications as follows. We say that the probability of the posterior, or the posterior probability, we replace the hypothesis with the symbol theta and the evidence with our data. So we say that the probability of theta given data is equal to the probability of the data given the parameter theta times the probability of theta, which is the prior probability, divided by the probability of data itself. Here, as you can see from this equation, that the data modeling, or the data parameters, is defined by the parameter theta, and this is maybe the easiest way to understand why we ignore the denominator on the right hand side, because the probability of data is 100% data modeling independent. It doesn't depend on the parameter theta, and this is why we can ignore it and both the posterior proportional to only the likelihood probability and the prior probability. So what is theta? We can understand theta as the parameter that defines the function we are looking for, that best describes our data. So you may think of theta as the set of coefficients that defines this function. It can be the set of slope or an intercept in a linear regression equation, or it can be the list of W, which is the list of coefficients that defines a polynomial or non-linear regression function. So theta is always expressing the parameters that describes our data and that best fits our data. Next, we will discuss the relationship between Bayesian modeling and probability distributions, and why probability distributions are always mentioned when we're talking about Bayesian inference. So, as you see that Bayes' rule or Bayes' theorem is a probabilistic equation in which each term in it is interpreted as a probability. And as a result, and in this context, the probability distributions arise as concrete tool in Bayesian modeling, because probability distributions are very well studied and well defined probability functions that can express the evolving of your data set in many different scenarios, and therefore the probability distributions is the cornerstone of Bayesian data modeling and of Bayesian inference in general. And in order to select the suitable probability distribution that best describes your data, you may first learn about your data domain, read a lot about previous scientific papers or previous case studies that describes data similar to yours, and try to understand how previous researchers handle this data domain. You may also want to visualize your data yourself and try to extract certain patterns that express the evolving of your data over time. So these are the ways you may use to understand your data and to select the probability distribution that best fits your data. Now we will begin with the first technique of Bayesian data modeling, which is the maximum likelihood estimation, or MLE. MLE is the simplest way of Bayesian data modeling. As I mentioned, this is the frequentist approach of Bayesian data modeling, and it is a special case of Bayesian data modeling in which we ignore both the prior and the marginal likelihood probabilities. And the formula of MLE is simply that the posterior probability is proportional to the probability of data given theta, which is the set of coefficients that you are looking to find. The procedure of maximum likelihood estimation is very simple. Actually, it's very straightforward. We start by selecting the probability distribution that best identifies our data, and in most illustrations we are using the normal distribution because it is very easy and very straightforward to understand and to track. The second step is to define random values of S and measure the corresponding likelihood values. And here it is very important to note that almost all Bayesian inference procedures are approximated algorithms, which means that we are not talking about closed form solution within the Bayesian modeling techniques, simply because we don't have a closed form or an equation. We are talking always about a proportional relation between the posterior and either the likelihood or the likelihood times the prior in case of the maximum a posteriori technique. So we always use this heuristic or this approximation algorithm in order to converge to the best likelihood value, and then we can consider it as the best coefficient to describe our data. So after generating random values of theta and measuring the corresponding likelihoods, we select the value of theta that corresponds to the maximum likelihood and consider it to be the best value that estimate the posterior probability or the posterior or the prediction that you are looking to generate. So let's take a simple numerical example to illustrate the MLE technique. Let's suppose that we have a company this company captures the blood glucose (BG) levels of diabetics and analyzing these levels and send its clients the suitable diet preferences based on the average levels, the average blood glucose levels of each patient. And suppose that we have a client that applied to this company, and she sent the BG readings for her for 1 week on daily basis. And after 1 week of inserting this insulin level, this blood glucose level, she asked the company smart application whether she can consume some desserts after her lunch or not. Her after meal blood glucose levels were 172, 171, 166, 175, 170, 165, and 160. So these are the 7 data samples that the company received from its client. And the question now is, what should the application recommend to this particular client? So the goal in this problem is to estimate the average blood glucose level to draw certain conclusion and send certain preferences to this client. So we will first assume the probability distribution that fits this data, and we will assume that the data was drawn from a normal distribution with an average of 168.43 and a standard deviation of 4.69, and these parameters were drawn from the 7 data samples that the company has received from the client. And we can draw this bell-shaped normal distribution with these parameters, and we see here that the mean of this distribution lies at the point 168.43, where the standard deviation is equal to 4.69. Now, after we make this assumption that the data were drawn from a normal distribution, we'll try to calculate the maximum likelihood using the data samples that we have. We'll say that the posterior distribution, the probability of data given theta, is equal to the probability of each data observation or each data measurement given the theta, and here we are maximizing the mean parameter. So we are setting the standard deviation as a constant, and we change the mean parameter of the theta in our case. So using the data samples, we have a fixed data average, which is the mean of the data sample, and we calculate the probability of each data observation against this average, which is equal to a probability of each data observation separately, given that the distribution was drawn around this average value. If we have a look at this graph here, we will see that we are trying to multiply the probability of this PDF against each observation of the blood glucose. And of course, if we multiplying these very small values, the generated result will be very, very small value, because you are here talking about a value will be very close to 0. And in order to come over this problem, we will replace the multiplication sign with the summation sign. And of course, this will not change anything in our estimation process, because the goal is not to have a certain value of likelihood, but the goal is to maximize the likelihood. It doesn't matter at which scale we are calculating these likelihoods. So we will replace the multiplication with the summation, And after summing up these small probabilities up for these 7 blood glucose values, we will find out that the maximum likelihood of this data samples is equal to 0.406. So it is about 0.41 value. Now, if you want to be more confident about the conclusion or about the estimation that we are making, we will generate 1,000 random values of theta in the same range of data samples. So we will generate 1,000 random average values between the minimum and maximum points of the data samples we received from our client, and calculate the corresponding normal distribution or normal probability density function. And the result of this value is as follows. As you can see here, after generating around 1,000 values of blood glucose values, we find that the average of this new distribution is at the point 169.55 with the maximum likelihood of around 0.41. And this is very close value to the estimation that we drawn using only the 7 observations that we received from our client. If we compare both distributions, we'll find that the difference is very small. It is 168 in the first sample distribution, and it is 169 in the or let's say around 170 in the second distribution. And the difference here is due to the data size, because here we draw our estimation using only 7 observations, but here we draw our estimation using 1,000 random values of the blood glucose, and this is why the both means are different from each other. But this is practically the way you can calculate the maximum likelihood estimation of your data sample and draw a conclusion to your client. So I'm not a diabetics expert, but I would think that the company may say that in this case the client can consume a very small piece of dessert after lunch with taking the suitable insulin dose. Now let's move to the second approach of Bayesian data modeling, which is maximum a posteriori, or MAP, or MAP for short. In this approach, we employ both likelihood and prior probabilities. So in this case, in our in the MAP techniques, we are employing 2 probability distributions. The first one is for the likelihood, and the second one is for the prior. And technically speaking, we deal with our data samples as if it were generated by the prior distribution, because here, if we understand the set of parameters theta as the set of coefficients that were used to generate our data, then the probability of the prior probability will be the marginalized theta probability over all possible values of theta. And in order to give also another numerical example, we'll continue with our example, and we'll suppose that the client updated the company after sending this sample data of these daily BG level readings for 1 week. We will say that, or we'll assume that the client updated the company with her historical BG levels for the last month, which turned to be 171 mg by DL on average, with standard deviation of 3. So in this case, we have another distribution which we will assume that this will represent the prior distribution of our problem. And in this case, after this update, we will ask ourselves how the company can use this new piece of information or this new probability distribution, if we can describe it like that, in order to update the blood glucose estimation and draw new conclusion upon this new information. In this case, as I mentioned, we have two distributions of blood glucose. One for the data, the 7 observations we received before, which represents the likelihood distribution, and the other for the prior, which is represented by the historical BG level for the last month. So, if you want to visualize these both distributions, we can visualize it very easily. We draw two normal distributions with the predefined mean and standard deviation of both distributions. This is the first normal distribution, which is the likelihood distribution, with the mean and standard deviation defined by the 7 observations we received in the first case, and the green curve represented the new update that we have received, which represents the in this context the prior distribution with the new mean and the new standard deviation. Now, in order to calculate the posterior using both sides, using both likelihood and prior probabilities, we will say that the probability, the posterior probability equals the likelihood probability, the conditional probability of data given theta, times the probability of theta itself. The first term we have already calculated before, but we need to multiply each term, each conditional probability taken from the likelihood distribution by the probability of theta itself. And how we calculate the marginal probability, the prior marginal probability of, which is P of theta in this context. P of theta here is the summation of all data probabilities over the prior distribution, which means that the probability of theta in this context equal to the probability of each data observation given the probability at theta, and we sum up all these 7 probabilities in order to obtain the prior marginal probability of theta to employ it in this equation. And in order to maximize the posterior estimation using the same technique as the same heuristic or the same approximation procedure, we generate new 500 random values of theta, again with a constant standard deviation and a variable mu over the same data range between the minimum and maximum of our data observation, and merge our random values in the previous equation. We will end up with this new probability distribution in black, and as you can see here, the average of the new distribution is equal to 169, which is some value between the likelihood and the prior estimations. Of course, it's very important to note here that the posterior probability is raised to some extent. This is something that I have done for visualization purposes, but it doesn't matter. The most important thing here is to understand the concept behind the maximum a posteriori. As you can see here, that we multiplied both distributions, both likelihood and prior distributions, in order to obtain the new posterior distribution. You may ask yourself why the new estimation of the posterior is closer to the likelihood estimation than the prior estimation. The answer to this question is that numerically speaking or frequently speaking, the likelihood estimation is drawn up on 7 different blood glucose values. We have here 7 different values that has been employed to generate the likelihood estimation. On the other hand, the prior distribution represent only a single value, a single blood glucose value, or a single observation at our data set. And this draws a very important fact about Bayesian inference, which is the bigger data you have and the larger data set you have in your problem, the closer the posterior to the likelihood will be more than to the prior. And this is a very important concept in the data analytics, and it is a very hot topic to be discussed between the people whom are more confident with the frequentism approach and the other team that is more confident to the Bayesianism approach. Is that as more as we have bigger data, as more as the final conclusion or the final estimation will be very close to the likelihood estimation. And if the data is going to be infinite, then the posterior would be typical to the likelihood, no matter what the prior estimation is. So this is a very important fact to understand in the context of the difference between Bayesianism and frequentism data modeling approaches. And to evaluate both maximum likelihood estimation and maximum a posteriori estimation, we can use a very common metric in this context, which is called the standard error. Actually, standard error is a very popular metric that indicates the reliability of a standard expectation or a standard average, and it is simply calculated as the average of the prediction or the predicted normal distribution. It is calculated by dividing the standard deviation by the root of the square root of the number of observation. And as you can see here, that the standard error of the posterior is 0.34, which is less than the standard error of the likelihood. And this gives us the understanding that the posterior distribution has been more confident and more generalized when we employed both prior and likelihood distributions, and it is more confident also to the client and to the final conclusion when we employ both distributions and both sources of information to calculate our posterior. This was everything in this video, and I would like to thank you very much for your time, and until we meet in next episodes, I wish you all the best. And if you have any questions regarding the material of these videos, please leave your comment below and I will do my best to answer it. Thank you so much.